Hello friends, welcome back to Webronaq. In this video, we're going to write a simple C++ program that calculates the area of a rectangle. Now on the surface, this looks like a basic math exercise. Length times width, done. But here's the interesting part. When you ask a computer to do this, a lot is actually happening underneath. The numbers you type get stored in memory, the multiplication runs through the processor, and the result comes back to you in a fraction of a microsecond. So while the formula itself is simple, the journey of those two numbers through the machine is where the real computer science lives. Let me show you how we put this together in C++. Alright, let's lay down the skeleton of any C++ program. At the very top, we write #include, angle bracket, iostream, angle bracket. This is us pulling in a library. Think of a library as a pre-written toolbox, someone else built so we don't have to. The iostream toolbox gives us the ability to read input from the user and print output to the screen. Without it, our program would be deaf and mute. Next line, using namespace, std. This one's a small convenience. C++ keeps thousands of built-in names organized into groups called namespaces, and std is the standard one. Writing this line tells the compiler, hey, when I use a name, check the std group first. It saves us from typing std : in front of every single command. And then we have int main, open parenthesis, close parentheses, open curly brace. This is the entry point, the front door of the program. When you run your code, the operating system literally looks for a function called main and starts executing from there. Everything we want our program to do goes inside those curly braces. Now let's add the actual logic. Now look at this line, float length, width, area. With this one line, we're doing something pretty important. We're telling the computer to reserve 3 slots in memory and reserve them right now. Each slot will hold a number, and we've given them names, length, width, and area, so we can refer to them later in the program. The word float tells the compiler what kind of number to expect. Float stands for floating point. That's the format computers use to store numbers that have decimal points, like 5.5 or 3.14. If we'd written int instead, we'd be limited to whole numbers only. And since a rectangle's sides might be 4.2 meters or 7.8 centimeters in the real world, float gives us that flexibility. Here's what's actually happening underneath. Each float takes up 4 bytes of memory. That's 32 bits the computer sets aside in RAM, ready to be filled. Right now those slots are empty, just placeholders waiting for values. The variable names length, width, and area are really just human-friendly labels the compiler maps to actual memory addresses. You read length, but the CPU sees something like address hexadecimal 7, FFEEABC. Same thing, different language. Let's fill those slots next. Now here's where the program actually starts talking to the user. We have cout, quote, enter length : quote, semicolon. Cout is short for character output, and it's our way of printing something to the console. The symbol is called the stream insertion operator. Think of it as an arrow pointing into the stream, pushing our text out to the screen. Right below it, we have cn, length, semicolon. Cn is the opposite, character input. The is the stream extraction operator, pulling whatever the user types and dropping it into our length variable. The arrow points toward length, because that's where the data is flowing. So this little back and forth, print a prompt, wait for the user, store the answer, is the most fundamental conversation pattern in programming. The same pattern is happening every time you type into a search bar on Chrome or send a message on WhatsApp. The program prints something, you respond, and the response gets parked in a variable somewhere in memory. We repeat the same 2 lines for width, and now both our memory slots are filled with real numbers. Time to do the actual math. Alright, here comes the heart of the program. Area equals length times width. 1 line, and it does the entire job. The equals sign here isn't the mathematical equals you're used to from school. In programming, it's called the assignment operator. It means take whatever is on the right side, compute it, and store the result in the variable on the left. So the computer reads this line and goes, okay, fetch the value sitting in length, fetch the value sitting in width, multiply them together, and drop the result into the slot called area. The asterisk is C++ syntax for multiplication. We don't use the time symbol you'd write on paper, because the keyboard doesn't have one. Asterisk became the universal stand-in across almost every programming language. Now here's what's really happening underneath. The CPU has a tiny built-in unit called the floating point unit, sometimes called the FPU. It's a specialized circuit specifically designed to multiply numbers with decimal points really fast. When this line runs, the values of length and width get loaded from RAM into the CPU's registers. Those are ultra-fast storage spots right next to the processor. The FPU multiplies them in a single instruction, and the result travels back out to the memory slot we labeled area. All of that, fetching, multiplying, storing, happens in nanoseconds. By the way, this same multiplication is what powers the physics in your video games. the pixel calculations in Photoshop, and the spreadsheet formulas in Excel. Different scale, same operation. Now let's show the result to the user. And now we finish the job. Cout, double less than, quote, area equals, quote, double less than, area, semicolon. Notice how we're chaining two things into the same cout statement. First we push out the label, the text area equals, and then we push out the actual computed value sitting in our area variable. The double less than works like a conveyor belt. You can keep stacking items onto it, and they all flow out to the console in order. Right after that, return 0. This little line is the program's way of saying, I'm done, and everything went fine. The 0 is a status code that gets handed back to the operating system. 0 means success. If we returned a different number, like 1 or 2, that would signal something went wrong. This is the same convention used everywhere in computing. When a script fails in a terminal or a build breaks in your CI pipeline, somewhere underneath, a program returned a non-zero exit code. And that closing curly brace wraps up main. The program ends, the memory we used gets released back to the operating system, and our rectangles area sits on the screen for the user to read. From declaring variables to multiplying them through the CPU to printing the result, the entire round trip happened in less than a millisecond. Pretty simple, right? But underneath those 8 or 9 lines, there's a whole symphony of memory allocation, processor instructions, and stream operations working together. That's the beauty of high-level languages. They let us think in terms of length and width, while the compiler quietly handles the bytes and the registers. Here's the interesting part. Want to leave you with. The formula we just used, length times width, looks trivial. You learned it in primary school. But there's something deeper going on. And it's worth knowing, because it shows up everywhere in computer science later. That multiplication is actually the simplest case of an integral. In calculus, when you want to find the area under any shape, a curve, a wave, a weird blob, you break it into infinitely many tiny rectangles, find each tiny area, and add them all up. That process is called integration. For a regular rectangle, all those tiny pieces are uniform, so the math collapses down to just length times width. Same idea, simpler form. This matters because the moment you start working with graphics, physics simulations, machine learning, or signal processing, you're computing areas under curves all the time. A game engine integrating a character's velocity over time to figure out the new position. A neural network integrating tiny error signals during gradient descent. A graphics card integrating light contributions across a pixel. Underneath all of them, the same primal operation we just wrote in C++. Multiply 2 numbers, store the result. So this tiny program isn't really about rectangles. It's your first taste of how computers turn continuous math into discrete operations. And every program you write from here on out is building on this exact idea. That's it for this video. If this gave you a new way to look at a familiar formula, hit that like button, subscribe to Webronaq for more videos that show you the computing reality underneath the code, and drop a comment telling me which topic you want me to break down next. See you in the next one.